Space Exploration. Epic ending. Spoilers ahead. Let's do this. First spoiler. Epic ending? What epic ending? The epic ending is at the anomaly. You find the anomaly with your 11th Deep Space Zone Discovery research. The anomaly is not on the galactic map. It is, somewhere nearby. You can see it from the universe menu, but the game won't tell you how close it is. It will give you an accurate time travel estimate until you leave normal space. After that, travel time will be garbage. But you can open the position section, and when spatial distortion reaches 10,000, you will be there. When you first reach it, it looks like this. But you can move the puzzle pieces until it is whole. Second spoiler. If you're thinking about doing the epic ending, what should you expect? To solve the epic ending, you will need to visit most of the pyramids across different stars and collect pictures. You will need 60 gigawatts of power at 8 different stars. This almost stopped me, but I did the math and I would be able to do a star every hour or two. You need 90 gigawatts of power at the anomaly. This is almost worse since you can't use solar power here. Ugh. I built a single antimatter reactor chain. It worked, but barely. You need to be a serious math nerd and like puzzles. You need to be comfortable with vector algebra in 3D. To make my dad happy, I got a master's degree. It was in 3D graphics where I learned many useless concepts like truncated icosahedron, triangular tessellation, and geodesic domes. All of these concepts apply to this puzzle. You need patience and a willingness to learn to recognize and maybe name most of the 60 glyphs in the pictures. You will also need software to OCR read numbers from Factorio screenshots because you can't cut and paste critical text. There are websites that will let you do this for free. Finally, anything you figure out with the pyramid pictures won't make sense until you unlock technologies that only appear after you construct and power the anomaly. Then they might start to make sense. Patience will be required. Final section. Full spoilers, one step at a time. The pictures on top and bottom of pyramids are not related to each other. They are for two completely different steps of the final puzzle. When researching long-range star mapping, you get 3D coordinates for the glyph constellation you should already recognize. The cost of research goes up exponentially, making it only practical to research a dozen or so. Making sense out of these coordinates is far easier if you can visualize them in 3D. I used GeoGebra for this. Here is the anomaly. If you dial in 8 glyphs, it tells you where they go. Usually it sends you a lot of biters too. I power it down immediately after dialing to avoid this problem. Where are you going? For that, you look at this entry in the Informatron. Then you guess the direction described was taken by this unfortunate ship and that you want to go back to wherever it came from. So the negative value of this vector is your target. Maybe you need to go back so you can fire the idiot that destroyed the anomaly? Here is a visualization of the constellations I researched and my target vector. I need to find the constellation that is closest to the target. Looking at the coordinates, it is clear there's a pattern to them. You will need to figure out the pattern and compute other nearby coordinates. After a while, it becomes clear the pattern is the same on both sides of the x=0 plane. So you can reflect points over that plane to make more. The same is true for the y=0 and z=0 planes. Reflecting a lot of points, things fill in well. This looks familiar. Aha! It is clearly a truncated icosahedron. This is the normal icosahedron, and this is an icosahedron on drugs. For polyhedra, truncation is when you flatten the vertices. How much you flatten is up to you. Yep, the Space Exploration star system lives in the middle of a soccer ball. Checking distances, X11 is the closest one to my target. But which constellation is that? Now we use our pictures from the pyramids. The points labeled P something are the ones we know from research. I call this constellation Not. If I look at it from the direction of the origin, I will see what those constellations look like when viewed from Novice. Rotating, so the pentagon is at the top, we compare the view to the pyramid picture and the other 4 mapped constellations. From this view, we can see where the 4 constellations show up in the picture. What do you think the odds are that X10 is this constellation? It is. Likewise, the pentagon constellations are these, and the other hexagon constellation are these. Knowing that X1 is this constellation, we use the picture from that pyramid. Now, I can work my way around to X11, and it is the wheat stalk. After providing power to the anomaly, 60 gigawatts to 8 different stars, and the needed coolant, the anomaly will power up. You can now dial in a coordinate using 8 of the 64 glyphs displayed. You use the R key to stop and start rotating the dial. You also use the R key to lock in glyphs you want. To reach the buttons and the glyph locks, you have to zoom out. That makes the glyphs kind of hard to see. Deal with it. After locking all 8 glyphs, it tells you what vector you generated. Our first glyph will be the wheat stalk. Now, onto the bottom part of the pyramid pictures. Each one shows 4 triangles, sometimes pointing up and sometimes pointing down. After looking at a few, you will notice they overlap. And some are identical but rotated. I drew this map of all of them, and this overlay, which shows which glyphs go where on that map. There are 60 pyramids and glyphs that can be discovered, but this map has 64 triangles. You won't find a pyramid glyph for any of these triangles. But this tile displays 64 glyphs, including these 4 new ones you won't have ever seen before. It's pretty obvious where they go. The first glyph dialed selects the constellation we are aiming towards. The next 7 glyphs use this triangle map to recursively narrow in on the exact target location near the constellation. First, we need to put our constellation in the middle of a triangle. The triangle's corners are the centers of the 3 polygons our constellation connects to. From the perspective of novice, we name the center of the pentagon N for north, the hexagon to the right will get E, and the one to the left W. Every polyhedron has a dual. The vertices of a polyhedron corresponds to the faces of its dual, and vice versa. The icosahedron has 12 vertices and 20 faces. Its dual is the dodecahedron, which has 12 faces and 20 vertices. If you stellate the faces of the dodecahedron, but only make the pyramids about this high, you get this thing that somebody named. This is the dual of the truncated icosahedron. Instead of having 60 vertices, it has 60 faces. Sorry, I lost myself there. All that matters is that we now have the triangle for the wheat constellation, and we can start computing our next 7 glyphs. This is our triangle and target. These are the grid lines that we will use to find our next glyph. Look familiar? We will recursively tessellate our triangle into smaller and smaller pieces until we have entered all 7 glyphs. This is how a geodesic dome works. You start with a polyhedron, you tessellate the faces, then you project them to a sphere. But this approach is flawed. To see why, I'll simplify to dividing a line rather than a whole triangle. Dividing the line up evenly looks fine until you project those points onto a circle. It doesn't look too lopsided if P1 and P2 are close, but if they're far apart, then C2 and D2 are looking bad. This has to be wrong. If someone a novice was dividing up space, they would divide it up evenly from their perspective. The fix is to subdivide the angle rather than the line. In 3D, this approach is called spherical tessellation. When applied recursively, it looks something like this. All of this matters because our math will need to be accurate enough for 7 glyphs. Alright, with 64 choices, each glyph provides 6 bits of information. With 8 glyphs, that's 48 bits. Since a sphere is 2-dimensional, we can divide by 2, and we get 24. That's the number of bits of precision each coordinate will need. 2 to the 24th is about 17 million, which is 8 or 9 digits of accuracy. Even small errors in how our tessellation matches what the mod is doing will cause our answer to drift from the correct one. While solving this puzzle, I wondered where the pattern on these triangles came from. Then I wrote this Python code to recursively spherically tessellate to our target. It divides the first triangle into fourths and picks west. It does this 2 more times, and our first glyph will be west, west, west. This one. But wait, that one has 3 lines on one side. Do those 3 lines somehow mean west, west, west? Sure enough, when you recurse north, west, or east, you draw a line on the side you picked. When you recurse the center, you draw a circle and the triangle turns upside down. West, north, east has lines on each side. Center, center, center is just 3 circles. Nice touch, Arundel. When I ran this Python code, it got the first couple of glyphs right and then drifted from the correct answer. Space exploration is not doing spherical tessellation. Arundel, what the heck? I might have to file a bug. I then used some nutty GeoGebra code to pick glyphs doing planar tessellation and give me coordinates for the next triangle so I could recurse further. It did better, but was a little bit off. I was still missing something. I thought about solving this with Factorio circuits, but that doesn't sound sane. I need 24 bits of precision, and Factorio stores 32-bit numbers, which is enough. But Factorio doesn't do floating point, so I'd have to use fixed point. I'd store 0.9998123 as 9981234 and pretend there's a decimal point here. 30 bits of precision should be plenty. But I need to multiply these numbers, and Factorio doesn't do that. If I just multiply these numbers, I get nonsense. To multiply them as fixed point numbers, I'd have to break each one into pieces, multiply the pieces, and add them back up. Something like this. But that would be crazy, right? So this pile of circuits solves 1 level of recursion, and I need 21 levels. Though I could use a clock and use this circuit recursively. It fails on the 10th recursion. This number here should be positive, and it should recurse north. The problem is this cross product. It's too small and losing precision. Each coordinate is the difference between 2 large numbers. R, for instance, comes from this plus 30 million and this minus 30 million. Those numbers have good precision, but they're not far apart, so when I put them together, I'm stuck with just 15 bits. It's just not enough. Then I made this 1-line change to my Python code to switch from spherical tessellation to planar tessellation, and the strangest thing happened. It got the answer exactly right. Wait, what? This code should be the equivalent of my GeoGebra logic. What the heck? Digging around, I found the key difference. The Python code normalized the corners of the initial triangle we started with. My GeoGebra code was just using the centers of the polygons. Ha! Mystery solved. Remember, those small errors add up. Mathematically, you need to take the centers of the polygons, normalize them, then recursively subdivide that triangle 21 times, and you can compute the next 7 glyphs. Okay, back to GeoGebra. This time I'm using the normalized coordinates for my starting triangle. At each level, this script would tell me which glyph to use next and what to change my E, W, and N coordinates to for the next level. I'd copy them the same way I copied Factorio numbers, grab a screenshot, and run it through some free OCR software website. Then I update my coordinates and repeat. This time, it gave me the right answer. I'll include a link to my GeoGebra calculator in case anyone wants to use it. You'll need to set T as the target from your game, and the normalized values for E, W, and N after computing them in the previous step, so still pretty complicated. You know, if I divided the cross product by the absolute value of the largest coordinate, yeah, that's insane, because Factorio doesn't do that, but this pile of circuits can. I'm still missing some precision, but now the dot product should have more precision, and that works much better. Still, the 15th recursion gets the wrong answer. This cross product is now below 10 bits of precision. I scale it up, but too much information has been lost. Alright, never mind. So, how many of these pyramid pictures do you actually need? When I first decided the wheat stock was X11, I entered these 8 glyphs to double check. This series of glyphs says to start with the Wheatstock constellation, then stay exactly in the middle of it 7 times. The value that came back was identical to X11, so it must be correct. You don't need the pyramids to figure out where the constellations are. You can query them all one by one, but that would be a bit annoying. As for the glyphs on the triangle, I was missing one I needed, so I entered these queries. Each one used the Wheatstock constellation. The glyph I was uncertain about then stays in the middle of it. I put the resulting coordinates into GeoGebra to see where those glyphs landed. So you don't technically need any of the pyramid pictures if you want to figure them out later. But each pyramid comes with a top-tier module, and dialing the gate is only fun the first time. It gets pretty tedious. I recommend collecting most of the pyramid pictures and dealing with the gaps later. You know, instead of scaling up the cross products, what if I just maintained an extra 32 bits of precision like this? Then I could use this barrel shifter to pull bits over if my cross product wasn't scaled to at least 10 million. Ah! Somehow that worked. I think I'm down to just a handful of bits of precision with the difference of dot products, but since I just care about it being positive or negative, I guess that's plenty. The epic ending was very creative and I enjoyed it. Dialing the gate is pretty tedious. You have to zoom out so you can see the buttons and the glyphs you're trying to load, but then they're small and hard to read. And learning over 64 glyphs that I planned to forget was annoying. Dialing the game 20 plus times is a bit grindy. I wish there was a way to dial it with Factorio circuits. And I wish there was a way to copy text from the Informatron. Using OCR to copy numbers out of Factorio is kinda lame. Other than that, I'm glad I did it. Space Exploration really is the best Factorio overhaul mod.